אז אני אציג אותך בעברית.
בטח.
אז שלום לכולם, ברוכים הבאים לסמינר האחרון שלנו לסמסטר זה. אנחנו עובדים עכשיו על התוכנית לסמסטר הבא וכולכם מוזמנים. הדוברת שלנו היום היא פרופסור הדס קרס גזית מקורנל. היא עכשיו היא הפרוגרמר של איקרא, והיא בין הרובוטיקאיות והרובוטיקאים המובילים בעולם. והיא הולכת לדבר איתנו היום על verifiable robotics, נכון? משהו כזה.
משהו כזה.
כן, הדס, בבקשה.
תודה רבה. תודה רבה שהזמנת אותי, ארז, ממש כיף. כמובן שהייתי מעדיפה להיות בחיפה עכשיו, אבל כן. טוב, זה קבוצה יחסית קטנה, אז ממש אני ממש מעדיפה שזה יהיה שאלות ודיון וכל מיני דברים כאלה. אז יש לי 40 וקצת שקפים, לא חייבת לעבור עם כולם. A few things. אני בארצות הברית מאז 2003, כל ההכשרה שלי אחרי התואר הראשון, תואר ראשון בטכניון, מחשמל, כל ההכשרה שלי בתחום המחקר שלי זה באנגלית, אז אני הולכת לתת הרצאה באנגלית, כי אני לא מסוגלת לעשות את זה בעברית. שאלות בעברית, תשובות, בטח חצי עברית, חצי אנגלית, סבבה, אבל bear with me, מה שנקרא. אוקיי, אז מעכשיו אני אעבור לאנגלית. נתחיל בזה. סבבה share. אתם רואים את הפרזנטציה, נכון? לא את הספיקר ויו.
כן.
קורקט, יופי. טוב, אז כן, הדס קרס גזית, אני גרה באיתקה, באיתקה ניו יורק, זה איפה שקורנל נמצא. Before I start talking about my own research, I just wanted to do a quick plug for Cornell. כשהייתי בארץ, או אפילו כשהייתי בדוקטורט שלי בפילדלפיה, לא ידעתי איפה קורנל. אני חושבת שאני מתחשב בזה ששומעים הרבה עברית פה, אני כנראה, יש הרבה אנשים שכן יודעים איפה זה קורנל, אבל רציתי להגיד לספר קצת לגבי קורנל עצמה. אני חושבת שעכשיו הטכניון גם כן עם כל ה-Jacobs Institute מכירים יותר, אבל סתם לתת לכם איזה kind of view of the land מבחינת קורנל. קורנל is an Ivy League in Ithaca, ניו יורק, 4 שעות נסיעה מניו יורק סיטי, מקום מהמם, קצת חור, אבל מקום מהמם. יש לנו קמפוס גם בקורנל טק, שזה בניו יורק סיטי, זה הג'וינט, יש קורנל טק זה בעצם ג'וינט, לא יודעת, ארז ודים, אני לא יודעת אם אתם יודעים לדבר על זה יותר טוב ממני, אבל קורנל טק,
Jacobs Cornell Innovation משהו, כן.
Cornell Tech has Cornell faculty and it has Jacobs Institute faculty, which is a joint thing between Technion and Cornell. Some of the faculty have lines in the Jacobs Institute, which means they have to have tenure Technion and Cornell, and the other side, the Cornell faculty only need to have tenure homes at Cornell Ithaca. These are the robotics faculty. We are across different departments, across different colleges, different campuses. So people in CS, I'm here. There's another one joining us here. There's another ECE and CS are both hiring this year in robotics, just to kind of give you a little bit of a feel of where we are. Cornell Tech, Cornell Ithaca. קוראים פה הרבה דברים. Okay, so now I'm going to talk my research. So I'm going to start off with a few projects that we've done over the years to just give you kind of a feel for the breadth of things we're looking at. And then I'm going to hone in and talk about synthesis. What does synthesis mean, or high-level synthesis mean for robotic systems? Okay, so again, I'm going to show you 3 seemingly random projects. So these are modular robots. These are built by Mark Yim at Penn, University of Pennsylvania. These are 10 by 10 by 10 centimeter cube modules that have 4 degrees of freedom, turning these 2 wheels, the pan and the tilt, it's kind of like a hinge in the middle. The faces have these half moons, which are electropermanent magnets. So these are magnets you can turn on and off. with a very short, very high current, which means that you can take these modules and configure them in different shapes, or create modular robots that have different shapes, different types of motions, and all that. And we had a project with Mark Campbell at Cornell, Mark Kim at Penn, and me, an NSF project, where we were thinking about how to do high-level behaviors for these kinds of robots. So for example, this is not the specification that we're providing, but just kind of as a way to illustrate. Look for a pink tag. If you find one, go there and drop off the object. So the idea is, given these modules, given this high-level specification, create these different behaviors that automatically create these different behaviors. So in both cases, it's doing the exact same task with the exact same modules, with the exact same library of configurations and gates. I'll talk more a little bit about that a little bit later. But you'll see the behavior is very different. The shapes are very different depending on the environment. And this is fully autonomous. Basically write a specification, hit enter, have the thing execute. So you can see on the left, it's seeing stairs. So it dropped a couple of modules. Again, fully autonomously. The reconfiguration is also fully autonomous. You can see the AR tags on top, the April tags on top. This is also sped up quite a lot. So this is ×8. Then it's reconfiguring. The left hand, it added those other modules to be able to move. On the right, it kind of create this kind of proboscis, so it can put something on top. But the point here is the same task, same building blocks, very different behaviors, automatically generated without any intervention. Different examples. These are Heavy Robotics. Heavy Robotics is a company that was spun out of CMU. It's one of Howie Chaucett's spin-offs. These modules are basically 1 degree of freedom modules that have continuous rotation, and you can compose them. So it has Ethernet, and it's a nice system. So given these modules, and given kind of the ability to connect them, so mounting brackets, links that you can create, and given 2 different types of tasks. So here the task is go through these points in space, or rather create a manipulator that is able to go through these points in space, the end effector, while avoiding all the obstacles. So anything in yellow, anything in green, and being mounted on this blue bar. Basically create a manipulator that can do that. On the other hand, it's also create a manipulator that can follow this gray trajectory. So it's no longer points, it's trajectories, while avoiding the red obstacles and maintaining and being mounted somewhere within these black rectangles. So this is, again, building blocks, tasks. And what we want is to automatically generate a structure and a controller that will do the task. So these obstacles are these red obstacles. It's drawing the rows that is drawn here and was created here using these shape primitives. Here it was going through those, the end effector was going through those waypoints without colliding, without self-collisions, without colliding with the environment, and so on. So those were more on kind of structure. The first one was structure and behavior. Here it's sort of more structure and controls. You can think about it going even higher level than that. Like, I have a robot. So there's a Baxter. This specific Baxter is at University of Rochester because it's a collaboration. This was a collaboration with Tom Howard and a student at Rochester. We have Gamnanish Baxters, but for now. And the task was pick up the blue block and drop it in the box on your right. Pick up the red block and drop it in the box on your left. Now this is the actual input. This is kind of a work. Tom does a lot of work with natural language. I've done some work with natural language, kind of, but this is the input. This is the robot we're dealing with. And here's the behavior that we see. Now it's not sped up, it's a little bit slow. Picking up the blue block. So, I mean, what's the point here? The point is you have to ground language to what the actual physical items are, but also figure out what the task is. Oy. All right, that's not supposed to happen. Oh my God, maybe I guess. Okay, it's picking up the blue block. taking it to the box on the left, sorry, the box on its right. You'd expect it to drop the blue block now, then go to the red. Nope. It's picking up the red, taking it to the box on the left, and only then, slowly.
Hadas?
Can
I interrupt for a question?
Yeah, please.
So what exactly is learned? What is planned? What is given, programmed? I mean, what exactly is the problem setup?
I'm gonna get to that.
Okay.
Nothing is learned. Well, actually, that's not quite true. Here, the grounding to the fact that blue block, what does blue block mean in terms of percepts, in terms of vision, in terms of RGBD, whatever, that is learned.
Mm-hmm.
Also, in this case, we're learning the connection between the language utterances and an LTL formula. I'll get to what LTL formulas are. That is also learned. But once everything is in LTL, then I don't know if I would call it planning because it's not the traditional type of planning. It's kind of somewhere hybrid between planning and control. Let me not use the word hybrid because that's very overloaded. Okay, so it's somewhere between, it's not classical planning in the IQ sense, but it is planning philosophically. So I'm going to talk a lot more about the planning. I'm going to call it synthesis, but that's the idea.
Okay.
מה שמביא אותי בדיוק למה שאתה שואל. So the common thing in these three somewhat different projects is that I have a set of building blocks. So I'm going to call this an abstraction. So I have pieces I can compose. These could be physical pieces, as in the case of the Hebbies, which are literally just modules. It could be pieces that also correspond to behaviors, and that would be the case of the modular robots, or it can just be controllers or behaviors, as in the case of the Baxter. So I have building blocks, abstractions, and I have tasks. I have some high level requirement or sets of requirements of what I want the system to do. It could be in the case of the Hebbies, it could be trajectories, could be points, it could be obstacles. That's kind of the way I'm defining my task. It could be a natural language utterance of a behavior. Typically, what I'm going to talk about the most is kind of somewhere in the middle, kind of a more formal specifications. Specifically, things I deal with mostly is different types of logics. So temporal logics specifically. All right. So roughly speaking, very roughly speaking, when you think about robotics and when you think about building robotic systems, and I'm not talking about, when you think about building robotic systems to do some task, for example, a robot to put on lipstick, right? There's some informal specification typically that gets given to an expert, or an expert has this internal informal specification of what the system should do. You design, and then you test. Okay, of course, there are some places, I used to work in Rafael. Informal specification is not quite the right word. There is very formal requirement documents, but these are documents written in Hebrew, right? So it's not a formal specification in the sense that I can take it and automatically translate that into a system. So that's why I'm calling it informal. It's not that it's not rigorous, but it's not, you cannot compute over it. Again, generalizing. The way I'm thinking about synthesis, and this kind of falls into also planning and everything, right? Is you have abstractions, you have these building blocks, and that was probably created by an expert, or combination of an expert and a less expert user, whatever. But the idea is once you have those building blocks, if you want to build a system, if you want to say what the system does, you would have to write a specification. And the idea there would be the specifications can be written by a non-expert. So this is my 16-year-old. I think this was when she was 14 or so. So super smart kid, not an expert in robotics. Can she write a specification? Right? That's the kind of the way I want to think about this. And then the idea is, in this kind of notion of synthesis, is you have these abstractions that were created somehow. These specifications that were given to you by the user, and then you automatically generate a design that satisfies their specification. Now, whether the specification is correct or not, that's a different discussion. We can talk about that. But given a specification, given a set of abstractions, synthesis will give you either a design sorry, in this case, the abstractions would be kind of the building block we talked about, and the task could be something like of these forms. But the nice thing about the thing I feel like is the strongest part of synthesis is the ability to provide feedback. If I cannot guarantee the design, I cannot guarantee you a design that satisfies a specification. Why? Okay, what are the things that will make you fail? And the feedback can take multiple forms, right? It can be either, I'm just going to tell you, can't do it because A. I might be able to rewrite the specification. And there's a bunch of work, not just from my group, but a bunch of groups in terms of rewriting specifications. I can't do this, but if you change this, I can do it, right? And then the hardest thing, but we do have a bunch of work, which I'm not going to talk about today, but I'm happy to follow up or take a tangent or whatever. You can take that feedback and actually modify the abstractions. So I'm missing a skill, right? I'm missing some controller to be able to do the full task. How do I identify that? How do I find that? And that's kind of more of my recent work, which I'm not going to talk about that today. We have a really cool paper that's almost ready to be submitted, so we'll see. Okay, so feedback is kind of where the strength of this. So I already know. I mean, I've been. It's interesting to see the evolution of this kind of subfield of robotics and the way it's accepted in robotics. So when I was still a PhD student, IROS 2007. Yeah, I gave a talk about my, some PhD, some of my a paper in my PhD work, and someone came to me and was like, "Yeah, I just don't like it. I just don't think it's, we tried this." That was a different person. Yeah, we tried this; it doesn't work. So the whole idea of providing guarantees and automating has gotten a lot more traction in recent years because I think a lot of our methods have become better. It still doesn't scale particularly well, but it's getting better. But also, I want to emphasize the fact that if you need to build one robot to do exactly one task and do that only that one task, synthesis is not the right way to do it because it's not necessarily optimized for what you need. You might not be able, depending on the specification language that you use, you might not be able to even capture the metrics that you care about. So this is not so much, I have a very bespoke, a very specific thing, I want to build a vacuum cleaner. Probably not the right way to do it. But if you have a manipulator and you wanted to, sorry for using kitchen metaphors, I actually don't like when people use it in robotics because we're not there. But, I want a manipulator that unloads the dishwasher and then cooks me an egg and then, puts all my groceries back in the fridge. That's a lot of different tasks. And I don't want to create a different controller for each one of them. I want to basically say, here's my specification, go do it. This is kind of an automation, if you will, of higher level behaviors, as opposed to solving one specific problem with the most optimized, most, best solution. All right, so that's my short speech on synthesis, why and why not. What I'm going to do now is I want to talk a little bit about the modular robots to kind of explain a little bit more what the abstractions were, what the specification is, what kind of feedback we can provide. And then I want to talk more, I want to give you a little more details about the synthesis algorithm. I'm assuming, I don't know if it's a good assumption to make, but I'm assuming none of you or most of you, actually, that's not it. Some of you have seen LTL, linear temporal logic. Some of you, I'm guessing not. So I'm going to talk a little bit about that. Some of you may have seen reactive synthesis. I'm guessing most of you have not. I'm going to talk a little bit about that. Then I want to show you a type of feedback that kind of formalism enables. Nahuatation, hon?
Okay.
Stop me at any point. Okay.
Okay.
All right, modular robots. These are what I meant before with the modules that you can combine. Oh, what are you doing? All right, anyway.
כשאת עושה share screen צריך ללחוץ optimize for video או משהו כזה.
לפעמים זה עובד, לפעמים זה לא. לא משנה, ואני לא חושבת לי עוד הרבה וידאוים. יש לי עוד כמה וידאוים. טוב. מקסימום אני אפסיק ואני אתחיל את זה מחדש. What you saw here is basically, I just wanted to show you what kind of robots we can build using these modular robots. In this case, it's a robot that can lower itself and move his body up and down. It has the way the modules are connected. It can also, it's basically a holonomic drive, so you can kind of turn the wheels in place and create this as a holonomic drive. So it's basically moving this box. So that's kind of just to show you the ability of those modules. But in terms of the building blocks are for the synthesis, for the high level behaviors, are not only the modules. Really, what we did there was, I'll talk more about reactive synthesis in a bit, but really what we had there is we had sensors, which we abstract. For example, stairs. So Mark Campbell, who was one of the PIs on this project, his students basically implemented a perception pipeline that can detect, stairs, cliffs, gaps. We had a kind of a sequence of a few things, a set of a few things it could recognize. So that would be the sensors. And then from the control side, from what the robot is, what we did is we created a library of configurations and gates. So configurations is the shape. So how are the modules connected? What is the graph that represents kind of the connectivity graph? And then the gates are, what are the periodic control inputs you provide to any of the degrees of freedom to create a behavior. So each configuration can have multiple gates, and each gate was assigned different properties. For example, the snake one could climb stairs but cannot turn. The other things that you saw can turn but can't climb. So we had kind of, and that was done manually. We did at some point. I'll show you in a second. So those are the building blocks. The way we created that library is we basically had a Unity simulator that we let a bunch of undergrads who are paid with donuts just basically create configurations and gates. Okay, let me just stop it for a second. The thing that's done. Okay.
עכשיו אנחנו רואים את הזום שלך כאן.
אתם רואים את הזום שלי?
כן, את your screen sharing.
אני צריכה לשתף אולי רק את המסך של המצגת.
לא, בסדר, אני רוצה לראות איפה אתם נעלמתם לי. אני רוצה, כאילו באיזה שלב... אתם רואים עכשיו פשוט המצגת, נכון?
כן, כן.
כן, אבל אני רואה, אני פשוט הפסקתי לראות אתכם. אני מנסה להבין איפה... הנה אתם, חזרתם. אוקיי, מוזר.
אוקיי, כן.
רואה אתכם. אוקיי, עשיתי optimize for video, so נראה מה קורה. אוקיי, טוב. Okay, anyway, we did this in simulation, the exact same controller, meaning the commands for the motors worked on the real system. So you can see kind of side by side. No, you can see side by side the simulated or the designed in simulation and the actual executed on on the actual physical system, where the stairs here are the same height, here they're not, different books, and so on. So we had about 52 configurations, configuration gates, and we used those basically to compose them in a way that will satisfy the high-level task. So what was the task? So this is LTL, so linear temporal logic, which I'll talk about in a couple of minutes. The blue are basically the abstractions coming from the sensors. So we had a perception system that says, okay, I see stairs, I see pink. I mean, OpenCV, seeing pink is not a big deal. Stairs, we're using RGBD cameras, so the depth to detect stairs. And then the specifications were over the attributes. So if I see stairs, I want to make sure I'm climbing. Climb can be mapped to multiple configurations and gates. Pickup object also mapped to multiple configurations and gates. And the idea is when you do reactive synthesis, really what you get at the end is a state machine that tells you, given this environment input, here's what I need to do. And in this specific case, the state machine is over these properties, which basically doesn't necessarily map to a specific configuration gate. So there's a connection between these properties and the library. And what we can do is a priori, ahead of time, right, figure out whether I'm missing some entries in the library. For example, if I see stairs and I see pink at the same time, I need something that can both climb and pick up an object. But I might not have a configuration gate that does that. So I can detect those things ahead of time. And that's kind of one of the types of feedback we can provide. In addition to, your specification is inconsistent, or the environment can make you fail this way, or there's a bunch of other things we can say. In this specific case, there's also the added bonus of saying, okay, I just don't have a shape and a control that can do this. So either tell me that this combination can never happen, or find me a configuration gate that can do that. Let's see. So this we already saw. This is exactly the same thing from before. I'm not going to run it again, as much as I love those videos. We've done these kind of using reactive synthesis, a different type of synthesis, well, actually reactive synthesis, for a whole bunch of different types of robots. So we've done this a little bit. I'm a little bit hesitant to say, I mean, we did run synthesized code on the Atlas for the DARPA Robotics Challenge. Didn't actually, I'm not in the competition. This was done kind of, long story, happy to talk about that. Baxter, the Nows, a couple of soft robots, simulation of a forklift in an environment. That's actually an Israeli student. Swarms, modular robots, manipulators, and so on. Also, shameless plug. We wrote it came out in 2018. There's a journal called Annual Reviews of Control. There's autonomous robots, autonomous systems and robotics, something like that.
Yeah.
I always forget the actual name of the journal now. I'm on the editorial board, so I kind of need to remember it, but whatever. It's Annual Reviews has the word control in it. Naomi Leonard is the editor-in-chief. She's wonderful. Anyway, so we wrote this is before I was on the editorial board. It's kind of this is a review of, as of 2018, of different approaches to doing synthesis for robots, if you're interested. Okay, so this is kind of, again, just pointing at the picture that we looked at before. I want to kind of explain a little bit what linear temporal logic is, very, very, very loosely. I'm not going to go into the, I want to give you the intuition. Then I want to give you the intuition behind reactive synthesis, what it looks like, and why I find it very suitable for robotics. And then based on that, I want to talk about one more type of feedback that we can provide. All right, linear temporal logic. I think I have this slide since I don't know, 2005. So not exactly this, I've changed the font, but you get the picture. So if you know what LTL is, you might be a little bit dismayed by the way I'm going to explain it, but if not, I think it's more intuitive. If you think about propositional logic, so and or not Boolean algebra, propositions have truth values. They're either true or false, and that's the world. When temporal logic, now the truth value of propositions can change over time. And once you have this ability, the truth value can change over time, you can write formulas over this kind of temporal behavior. For example, I can say, I always give the example of where I am right now. So Hadas in Ithaca is currently true. The formula Hadas always, so this square, always Hadas in Ithaca Hopefully it's false, because at some point I don't want to be here, right? So I like traveling. At some point the pandemic will end. Eventually Hadas in Ithaca is true, because I'm here right now. Eventually Hadas in Israel is probably also going to be true, right? Hopefully this summer, we'll see. So once you have this ability to talk about change over time, now it really is useful for dynamical systems, or systems that, decision making and all that. So eventually I want the robot to be in the room. Eventually I want the robot to pick up a plate. Always I want the robot to avoid crashing into the wall, and so on. You can so those are kind of goals, eventually. Safeties, always, but you can do much more complicated things than that, like reactions, or if this happens, then this should happen, and kind of any combination thereof. So that's LTL. There's a bunch of synthesis for LTL. The reactive synthesis is kind of slightly different, not different, but it's reactive synthesis was kind of introduced kind of in this paper by Turing Award winner Emil Pinoeli and Ronnie Rosno. The idea there is I have propositions, and I'm going to separate them into two groups. One are my inputs, and if you think about this in terms of robotics, sensors, environment, perception, and you have outputs, which again in the context of robotics will be controls, or behaviors, planning, or actions, skills, all these things you can think about. And then given an LTL formula over this set X of inputs and set Y of outputs, you want to automatically generate a state machine such that every execution of that state machine satisfies the formula. That's the notion of reactive synthesis. The word reactive comes from the fact that there are inputs that you don't control and outputs that you do. So you need to react to the inputs, which again, sounds very roboticsy, right? So this is an example from the original 89 paper, which I really like. So this is kind of to give a feel for how not for how it works, but rather what it is. So we have two propositions. X is an input, Y is an output. And my specification is, if X at the beginning of time is false, then I want all this to happen, okay? So I want Y to start out as false. I want always, if X is true, eventually Y will be true. And always, if Y is false, it implies that Y has to be false until X becomes true. That's this formula. Why this formula? I mean, why not? Right? It's an example. There are multiple different state machines that can satisfy this behavior. So it's not that there's not one unique behavior that will satisfy this formula. There are multiple. So this is kind of another thing to consider about writing specifications in LTL or higher level. You're kind of putting constraints on the behavior, or kind of what you want the robot to do, but there could be multiple ways to implement that. Some, you might have some ordering on how you like that, and then, or what optimality means here, but that's a different discussion. But this is one solution, right? The solution is, if X is false, then I'm going to, Y I'm going to keep, so again, X is something I'm observing, Y is something I'm controlling. So if X is false, I'm going to keep Y false as long as X is false. Once X becomes true, I'm on the wrong one. X is false, Y is false. Once X becomes true, Y becomes true, X becomes false, Y becomes false, and so on. So basically what I created is something that is an output that is tracking the input. I could have also added extra states here in which Y tracks X 2 steps later. That would still be a valid solution. But this is a solution to this state machine. Every execution of that satisfies the original behavior, the original specification. Now you'll notice that if X starts out as true, I don't have any transition here. But also, if X starts out as true, the left-hand side of the implication is false, and then nothing matters. By definition, this formula is true. So Y doesn't have to do anything. Okay, so that's kind of another thing to consider. So reactive synthesis for full LTL is not particularly tractable. It's a double exponential in the size of the formula. We don't like double exponentials. In 2006, Neil Peterman, Emil Pinoeli, and Yanil Zar wrote a paper, which were then they have the journal version with Roderick Bloom and Barbara Jobsman, where they define a fragment of LTL. They call it GR1, Generalized Reactivity 1, which has this very specific structure. And for that specific structure, it's polynomial in the state space. Still, state space can be humongous, but better than double exponential. So what does it look like? It looks like you have phi E, which is assumptions about the environment, implies phi S. Both phi E and phi S have additional structure in them. So it's not just any random LTL formula there. I'm just kind of not going into detail because I don't think it matters so much at this point. So we have assumptions, implies robot behavior. Again, it's implication. If the assumptions fail, then robot can do whatever it wants because by definition, the formula is true. If the assumptions hold, robot must do behavior, or rather, if I'm able to synthesize a controller, it means that no matter what the environment does, as long as it satisfies its own assumptions, the robot will do what is required. Again, under the assumption of abstractions and all that. So this is GR1 synthesis. A lot of the stuff I've done kind of works with this GR1 synthesis. Kind of the last thing I want to talk about in more detail is what happens when the assumption fails. Okay, so I'm baking in to the controller the fact that the environment satisfies the assumption. That's the way I'm constructing my controller because it's an implication. So I'm actually constructing a controller such that it either tries to falsify the environment, which is in some domains it's fine. For robotics, we don't want to do that. Or whatever the environment does, robot will satisfy its task. Now that's fine. You're making a whole bunch. We're making assumptions. We always make any system that you build, you make assumptions. Here, it's nice that you're explicitly stating what your assumptions are. The problem is what happens when you start executing and the assumptions fail. So before, if the assumptions fail, game over, right? Typically there would not be necessarily a transition in the state machine to be able to execute, or really nothing you can do, right? So some of the I had a student that did a little bit of work on this space, and what we did, we basically robustified the state machine against assumption violations sometimes, but also during execution we rewrote those assumptions to be able to be more robust to different observed behaviors. And I'm using, Aviv, to your question about learning, I'm using the word, I'm on purpose not going to use the word learning here, even though we're changing our behavior based on observed environment behavior, because it's not learning in the sense of trying to map a model to really what we're doing here, and I'll show you in a second, is we're going to take the assumptions, we're going to see, oh, this behavior does not satisfy that. Okay, so I guess this behavior is also allowable. So we're basically weakening the assumptions as we go. All right, so this is an example. Let's see if this video will work. Simple behavior, robot starts here, needs to go kind of into this area. This is part of the specification. So we have, it wants to always eventually be in the corridor. So it needs to get to the corridor. Always, if the door is closed, so there's going to be a door here. If the door is closed, it can't go into this region called door. But I'm assuming, this is my assumption, this is part of my assumption, that always, if the robot is in the hallway, the door is not going to be closed. That's my assumption. Why am I making that assumption? I made that assumption. Okay. So then if I'm executing, this is the state machine that I get from this specification plus a few more things that I'm not showing. Starting in the mailroom, the door is closed. Sorry, the door is not closed. Yeah, the door is not closed. There's no door. Suddenly it's in the hallway and there's a door. So again, we're recognizing the door using this radial barcode. This was not, the perception here is not anything, very cleaned up or made easy. But really what happened here is now I don't have a transition. In the hallway, I'm assuming the door is going to be open and I don't have a transition. So this red thing actually doesn't exist in my state machine. So I failed. So what we did is basically we added, during the synthesis process ahead of time, we're relaxing the assumption that the environment will always satisfy its assumptions. And we're also adding transitions labeled with environment assumptions that violate with environment behaviors that violate the assumptions, as long as it doesn't make the robot catastrophically fail. What I mean by that, if there's an assumption violation that is transient, so it will at some point resolve itself, these transition will just make the robot wait, and then once the assumption violation gets resolved, it's going to continue. So if it's in the hallway and it sees the door closed, even though I'm assuming it's not going to be closed, it's just going to hang out in the state. And then once the door opens, then it's going to move to door. So this is the recovery transition, even though this violates my assumptions. So this is what's going to be what's going to happen. It's basically going to hang out there. It's going to be in the state. It's going to be in the state until cat comes back and moves there she is, and moves the door. Video is not cooperating with me. Anyway, it's moving back to that. That's one thing. Robustifying the controller by adding behaviors that were not allowed, but might happen, as long as it doesn't make the robots catastrophically fail. And then we have the environment characterization. So this is us very explicitly avoiding the word learning back in 2018 or whatever. And the idea, the reason for the environment characterization, what we're doing there is we're observing the environment. We have monitors that monitor the assumptions. Anytime an assumption is violated, we do basically an OR. We add more possible behaviors, and then we resynthesize. So that's what's happening here, right? So same behavior, same task as before. No. Okay. The door is closed. It's fine. So we're seeing that currently, the door is open. So not door closed. We shouldn't have done on negation. So the door is open. It's going to hang. It's going to just kind of move, keep moving. And now, okay. Stop it. Okay, stop it. Now the door is closed. So now I'm observing that the door is closed. So now I'm adding to the environment assumption. I'm saying, okay, always, if the robot is in the hallway, the door is going to be open. That was my original assumption. Or the door is going to be open because that's what I observed when I started out. Or you know what? The door can be closed. That's another assumption I'm making because I saw that happen. So really, what happened here is I reduced the assumption to just be true. I have no assumptions about the environment. The door is either open or closed. Now, if I make that assumption, now I can no longer guarantee my task because the door might be closed forever. So now what I need to do is I need to go back to the user and say, you know what, can't do this. Is there any liveness, anything that you can tell me about expected future behavior that would make me be able to continue my task? So if the user says, you know what, this will eventually be open. Always eventually the door is going to be open. Then I can do my task, right? Oops. Move it here. Okay, so this is it, the door is closed. And we ask, the thing is, you can observe current behavior, but you can't observe future behavior, right? So if you want any liveness assumption, anything that eventually will happen, you have to ask a person. So here's the environment assumption. We added that, always eventually, okay, I'm just going to stop this. Always eventually the door will be open, and then the robot the robot is basically just going to say, okay, now fine. Now I'm just going to wait for the door to open because I know it's going to happen. And then they can continue. It can continue. So what we did after that is kind of with the same idea of kind of this, the environment can be something, like really that you can't control or influence, but you can also think about it as a multi-robot. So the other robot, so this is a non-collaborative multi-robot behavior. And you have maybe assumptions about the other robot, but those assumptions may or may not be true. Now, the nice thing about when it's multi-robot and presumably not adversarial is that you can communicate your assumptions and resolve conflicts that way. So in this case, what we did is orange is trying to go to the orange flag, blue is trying to go to the blue flag. they make an assumption that a robot will never be in the region it's trying to go into. So if the blue robot is here, orange is not going to be here until it's actually out, right? I don't know if it's going to work or not. Okay. I'm going to give up on videos, but the idea is, as the orange is moving towards square, they realize they have a conflict, and then they communicate their assumptions. And if one robot's assumptions work for the other robots that does not conflict with the other robot's task, they can just incorporate that into their own task and resolve the conflict. And again, everything here is fully autonomous, right? So they all have their task. Each robot is starting with their own task. We start executing, they detect a conflict, and they resolve it. Now, how are we detecting the conflict? We have a Vicon system. We know where they are. So the perception side here is not the interesting part. But the fact that it can automatically resolve it, that's kind of the interesting part. Okay, so one last thing, which is going to be a lot less technical, but I kind of want to put a plug in there. So in the spirit of kind of talking more about papers I wrote, this is Communications with ACM paper that came out in September. This is a result of a digital seminar that we ran in 2019, I guess, 2019. Time is a blur. So we had a digital seminar on formalizing and guaranteeing human-robot interaction. So the question is, these formalisms, for a robot, kind of for task, I can see that. I mean, we've done a bunch of things. There's a bunch of things to still be done, but it's a lot of the formalisms are understood in terms of perception, in terms of control. How do we formalize, how do we synthesize human-robot interaction when now the environment is a person? And modeling people is hard. What do you model? What specifications should you have? So we wrote kind of a position paper in terms of challenges that we see in this direction. And I've had a few kind of more recent papers, two of them with Guy Hoffman, who's at Cornell, one of them with Laurel Reek, who's at UCSD. That's the HLI one. And really, what are the right encodings? What are the right formalisms to use? LTL is really powerful, but it's a discrete logic. And then things like time, you can kind of capture the timers and everything. It's not a good way to do it. We've been looking at signal temporal logic, which is over continuous signals. We're looking at SMT encodings, which all of these have pros and cons. Really, the thing that we know that we need to kind of embrace is the fact that people are messy, right? So figuring out what are the right things to say there. And that's kind of something that I'm really interested in these days and kind of hoping to push on more. Okay, so 5 minutes till, to be fair, it's been 46-minute talk, so I feel okay. These are different snapshots of my group at different years and different lengths of hair for me. So left to right is the most recent is the one on the right. And yeah, and I'm happy to take any questions or discussion or,
Excellent. Thank you, Hadas. This was super interesting. So I had a question about the work you presented before, where you don't want to say that you learn, right? But you learn. So
no, I don't learn. Well, I don't learn because what I'm really doing is weakening assumptions.
Right. But you had two things you can do there, right? You can either weaken assumptions about the environment, or you can ask a human to give you actually stronger assumptions about the environment, right?
True, yes.
So how do you decide which of them you want to try?
Well, I'm going to try first to do everything autonomously, right? So I'm going to first add, so really what am I doing? I'm saying, okay, here's what I think the environment can do. Oh, I see something new. Okay, so I guess it can also do that because I saw it, right? So I'm going to add that. As long as that's still synthesizable, as long as I can still generate a control, I'm good. The problem is when it becomes unrealizable, because I should have mentioned this, reactive synthesis is a kind of a worst case. if the environment can do anything to make me fail, I won't generate a controller. So in those cases, the only thing that I can add, because I saw that behaviors, I can't remove those behaviors. So now the only thing I can add are kind of these fairness assumptions or kind of things that eventually have to happen with the environment, and that can only come from a person. Yeah.
Okay. And is there some notion of this is a better assumption to make than that because this is more likely to happen or something like that?
In terms of what we're asking from the person or what we observe?
In terms of what you observe, right? I mean, presumably you only observe the things that are more likely to happen, right?
Yeah, well, okay, so I think there are two layers of what you're asking. So one layer is, could there be other behaviors that I don't observe? Yes, but I don't know about them. Because I either have the assumptions you made when you wrote the specification or the things I've seen. If I didn't see it, well, to some extent, the recovery helps with that. Because if it's something that could happen and won't make me catastrophically fail, it's already encoded in there. So that would be okay. The other point, what we're doing, I didn't go into detail here, but we're actually adding, there are two layers of how much you weaken the assumptions, right? You can either say, here's what I see, here's what the environment, the door is open. Or you can say, well, if I'm in the hallway, I see the door is open, I can it's more constrained. Saying, okay, if I'm here, then I see this. So you can kind of play around, you can play with both of those. If you add also the state of the robot when it's observing it, then the assumptions are not quite as weak. But then you might have to go through it multiple times too.
Yeah. Interesting. Aviv, it looks like you have a question, right?
Yeah. First of all, thanks for a very, very interesting talk. I have actually two questions. The first is, do you have any idea how to use this, for example, in application? Maybe like current. I can definitely see how this be used, in future applications. But things that are current, in current industry and something like that, is that relevant? And the second question, which might be related, is how would this work if your perception is not accurate?
Excellent. I'm still sharing. Hi. Okay, so let me take them in order. So first, kind of application to current industry. So I guess my question is, what do you have in mind? Which industries do you have in mind?
I was thinking, I don't know, like robotic robots in industry, for example, e-commerce, logistics, things like that, or what are I don't know exactly what this could be useful. So that's basically the question.
Well, what is it useful for? Okay, so I have a cynical and less cynical answer. So things like logistics, actually, this would be very useful. It's not deployed in any place, right, that I know of. Some of these techniques, not so much the reactive synthesis, are really of interest in like self-driving cars. So kind of providing guarantees for self-driving cars. You can think about this, reaching somewhere while avoiding pedestrians. Well, there's a bunch of things that actually work out very well for this. So self-driving cars, logistics, kind of warehouse automation, that will make a lot of sense. Things that are kind of single robot, single task, that doesn't make sense for that. So the Roomba doesn't make sense, right? The whatever kind of household robotics would make sense. Arguably, there is no household robotics yet. But that would make a lot of sense for that. So those are kind of the things. Robots that have different, also kind of swarms, but again, there's no current application for swarms.
Yeah, that what motivated my question exactly.
Yeah. I guess Kiva, right, or Amazon Robotics. That could make sense, but there it's a very specific task. And they care a lot about optimality of trajectories. And it's not that this doesn't really lend itself that well for optimality at this point. So I don't know that the kind of Kivas or whatever Amazon Robotics type thing, that doesn't quite make most sense. But if you want swarms operating in different environments and doing different tasks, and we have a few papers on swarms, that would make sense. But again, it's not a current application, but hopefully, the next 5-10 years, maybe. I don't know. The other thing, the more cynical thing is, I'm an academic. I cannot compete with industry.
Yeah, you don't have to tell me that.
Yeah, so my job is to think about, the next 20 years. And I think there are a lot of, again, this is not yet scalable. You need a lot of engineering effort to make this really usable in industry. But I think it's engineering effort as opposed to conceptually understanding what the problems are. I think for HRI, I think we're still at the kind of conceptually, how do we even address that? So that's why it's really exciting for me. Plus, I really like Guy. So always fun working with friends. The other thing you were asking, perception. Yes. So excellent question. I have a big project working around the fact that, perception sucks sometimes. Well, let me not go that far, but sorry if Vadim is still there. There's a lot of uncertainty. So there are probabilistic logics where you can incorporate. We actually we just had a paper accepted to HSCC on probabilistic verification of STL formulas. So there are probabilistic logics. It's kind of, yes, it's of interest. There are things, the LTL reactive synthesis is very kind of yes, no. But you can kind of encode, well, ultimately you're going to make decisions, right? So you're going to take a perception pipeline, and you're going to make, at some point you're going to put a threshold, or maybe do it smarter than putting a threshold, but you're going to say, yes, I see stairs, no, I don't see stairs. And once you have that, then the only thing, the thing you want to think about is, I'm going to take your decision. I'm going to the whole synthesis is going to, the whole control is going to be based on that decision. And now what you can do is you can analyze what's the probability of you failing based on your perception system, on how you made that decision about the perception.
I mean, I'm not sure I agree with you, because that's not the only way it can work, right? It can also work without knowing if I see stairs or not, and not ever making that specific distinction, the decision.
So you were saying the task will not depend on that specific information.
I think maybe
when I'm walking up the stairs, I don't know if I stop to think about, are these stairs or not?
No, but I think another way to look at it is, if I think I see stairs but I'm not sure, maybe what I need to do is go closer and check, right?
Yes.
And increase.
But that depends on having kind of a concept for stairs.
Yes.
So having a good concept that you can actually, it might be that stairs is a good concept. It might be that I don't want to define stairs, because there are some things that look like stairs that I don't need to treat them as stairs, or they might be places that I need to walk on. I don't know, like if I'm in a natural environment and there are no stairs, nothing looks like stairs, but that doesn't like as a human, I don't care about walking, נדבר בעברית רגע, כן,
כן, דבר בעברית, אני מבינה.
לא יודע למה דיברתי באנגלית בכלל עד עכשיו. אז אם אני הולך בחוץ, בטבע, ואין מדרגות, זה לא מפריע לי בשום צורה. נכון, הקונספט של מדרגות זה רק אולי מסבך אותי. אם אני אחפש מדרגות ודברים שדומים למדרגות בחוץ, יהיה דברים שהם לא בדיוק מדרגות, ואני צריך להחליט אם מדרגות או לא מדרגות, אבל בשביל לקבל החלטה לאן ללכת, אני בכלל לא צריך את זה.
מסכימה איתך לחלוטין, אבל מה שאתה מדבר עכשיו על what is the right abstraction,
כן,
what is the right set of building blocks, וזאת שאלה קשה, זאת שאלה שאין לי תשובה, I don't have a general answer for that. I have, because it's very task dependent, and what you want the system to do, and where you want it to operate, so environment and task dependent. So where do we get good abstractions? Excellent question. And I don't know that anybody has really good answers for that. There is a bunch of work on grounding symbols, but even then, if you're learning symbols from data, you still have to choose features. So
אני לא בטוח שזאת כלומר, אני לא אגיד שיש משהו שכרגע עובד ממש טוב, אבל אני חושב שהגישה מעולם של הלרנינג אומרת בדיוק הפוך, אני לא רוצה שיהיו לי פיצ'רים, אני רוצה לעבוד ישירות על ה-perception, ותני לדאטה להחליט לבד
מה הדאטה? עזוב, מה הדאטה? איזה דאטה אתה מכניס?
מה שהרובוט חווה באיזשהו...
כן, אבל עם הגישה שלך, אתה לא יכול להבטיח שמכונית אוטונומית לא תעשה תאונות, נכון?
כאילו ברגע שיש abstractions, then you can start talking about it, about what you can guarantee and what you can't guarantee. אבל להגיד ש-machine learning זה פשוט אתה זורק דאטה ואין שום hand tuning של features, אני לא חושבת שזה נכון.
יש איזשהו hand tuning, אני לא יודע אם זה של features, אבל של משהו, כן, יש הרבה מאוד, כמובן, כן, ברור שזה לא, שום דבר לא אוטומטי באמת, אבל למשל בקומפיוטר ויז'ן, יצא שאת הדברים הפריצות דרך קרו כשהפסיקו לנסות להגדיר בדיוק את מה יש בתמונה ומה אין בתמונה, נכון?
לא נכון, כי היה להם המון label data. מה זה ה-labels האלה?
לא, אז היום יש הרבה דברים שעובדים unsupervised, נכון? כלומר, כל אז תגידי, ובצדק, שגם שם יש איזשהו ידע מוקדם, הם עושים טרנספורמציה, אוגמנטציות על הדאטה ודברים כאלה, וזה נכון, אבל נראה שככל, ההתקדמות מושגת ככל לפחות בקומפיוטר ויז'ן, ככל שמורידים את הידע המוקדם ולא ההפך, אבל אני מסכים שנהיגה אוטונומית כל זה בכלל לא רלוונטי, כן? אבל...
אני גם חושבת שברגע שאתה מדבר עם מערכת, ברגע שאתה מדבר על רובוט שצריך לעבוד ב-physical world, הרבה דברים שעובדים ב-computer vision will not work.
מסכים לגמרי.
אבל ה-question of abstraction is a very good question.
אני חלילה לא טוען שיש לי איזשהו כיוון של תשובה לגבי מעלה את זה בתור שאלה.
טוב, זה היה מרתק, ואנחנו יכולים להמשיך פה בטח עוד שעה, אבל אני חושב שכדאי שנעצור. אז אני רוצה להודות שוב להדס, היה מצוין, ואני מקווה שנתראה אולי ב-KR 2022 בחיפה.
במה?
בחיפה, כן, KR 2022.
מתי זה?
שבועיים, מתישהו בקיץ הזה, אני אפילו לא יודע אם זה יקרה באמת או לא, אבל כאילו פיזית.
מה שנראה אתכם בעיקר, בפילדלפיה.
אם תקבלו את המאמרים שלי, אז...
אתה תדע ביום שני, מבטיחה לך שתדע ביום שני.
אוקיי.
עכשיו אני הולך להסתכל. לא, זה 3,300 פייפרס, לא הבנו נכון.
וואי.
כן. יש לי כמות מטורפת של אקסל ספרדשיטס, זה פשוט מזעזע. טוב, תודה רבה על האירוח. ואם אני הייתי בקיץ שעבר, אבל זה פשוט היה סיוט עם כל הסיוט. אבל אם